Okay, our last lesson in chapter 4 is our final technique to approximate a definite integral. So the trapezoid rule, recall that a Riemann sum, and you guys just, don't worry about copying this down if you don't print out the notes, all right? You already have these in your notes. A Riemann sum is a geometric approximation of a definite integral, okay, of some area bounded by the vertical lines x equals a and x is equal to b, some function, and the x-axis. So we looked at left Riemann sums, okay, where the left point of the interval intersects the function. We looked at right Riemann sums, where the right hand side of the interval intersects the function. Now this is from the textbook, but this little s of n, this would be our under approximation, and we know that the actual area is somewhere between our under approximation and our over approximation. Notice that these rectangles, more area lies above the function, and in these rectangles, all the area lies below the graph of the function. Okay, so remember what the area of a trapezoid is: 1/2 times the sum of the bases times the height, and we have used this a little bit when we were doing exact areas. The bases are always the parallel sides, and the height is always the distance between the bases. So now let's look at it in terms of a function. So the area will be 1/2. Look at the bases. The bases of the trapezoid come from the function values. So these are the y values of the function. And the height, the length, the distance between the two bases is b minus a. That's the difference of our interval over n, where n is the number of figures, the number of trapezoids used to approximate the area. Now the width of the trapezoids will always be equal. Is that right? All right, disregard that. They may not be equal if we're given a table of values, and we'll talk about how h will change for that. Okay, so the trapezoid rule, as with any definite integral, the function must be continuous on the closed interval. Okay, so let's think about what this says. Okay, so the definite integral between a and b, here's a and b, can be approximated using the area of a trapezoid. Area formula, 1/2. Now think about the height. For these, the height, we're using 1, 2, 3, 4 trapezoids. So n is equal to 4 for this example. The width of each trapezoid, or what we would replace the h with in the geometric formula, would be b minus a over n. Now let's check out the heights. The height of the function represents the base of the trapezoids, because again, all of these lines would be parallel to each other. F of 0, f of x sub 0, so that would be our value of a. So the bases of this trapezoid would be x sub 0 and x sub 1. If I look at my next trapezoid now, these would be the base of the next trapezoid. The third trapezoid, these bases would be f of x sub 2 and f of x sub 3. So notice what's happening. There will always be, for the trapezoids on the inside of the region, there will always be an overlap. Two trapezoids will share the same base. So to clean this up a little bit, we would have b minus a over 2n, multiplying these. We start at whatever our a value of the function is, and then we double the next function values until we get to b. So the coefficients for the y values at our endpoints will always be 1, and the coefficients in between will be 2, because these trapezoids on the inside will always share a side. Now check out how many things we're adding together. We would be adding 1, 2, 3, 4, 5 values together. So for your trapezoid rule, your number of y values is always 1 more than however many figures you're using to approximate the region. Okay, let's look at some examples. Use the trapezoid rule to approximate the definite integral. Compare the approximation to the exact value of the definite integral. Okay, so we're using 4 trapezoids. So our approximation, we'll set it up first. It'll be b minus a over 2n. And again, it always has to be 1/2 because of the area formula for a trapezoid. And now the function values we plug in, we start at a, so f of 0, plus 2 times f of. Now think about how we determined for left and right Riemann sums where the next value came from. The difference between here will always be our b minus a over n value. So the next y value I would plug into the function would be a 4th. And then 2f, when I add a 4th there, I get a 1/2, plus 2f of 3/4. And now when I add another 4th, I'm at the end of my interval, my value of b. So this was 1/4. So the width of each interval is equivalent. All right, this gives us 1/8. Now where do these values come from? We plug it back into the integrand. So this would be the sine of 0 plus 2 times the sine of pi over 4 plus 2 times the sine of pi over 2 plus 2 times the sine of 3 pi over 4, and then plus the sine of pi. So plugging in each of our x values into the integrand, and again this is still an approximation, so we can do this without a calculator. This would be 2 times square root of 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is also positive root 2 over 2, and the sine of pi is 0. So we would have 2 root 2 plus 2 over 8. And just so we can compare it, using a calculator, that's about 0.604. Get in the habit of 3 decimal places. Now it says compare it to the exact definite integral. So now that we've done u substitutions, u here would be pi x, which makes du pi dx. Solving this equation for dx and making my u substitution, I get the sine of u times du over pi. So 1 over pi is going to be my coefficient. Antiderivative of sine is negative cosine of u. It's a definite integral, so I don't need my plus c, but I will bring the negative out front, replace u with pi times x, and evaluate this definite integral from 0 to 1. So I have cosine of pi minus cosine of 0, negative 1 over pi. Cosine of pi is negative 1, cosine of 0 is 1, so this gives me a value of 2 over pi, and as a decimal, 0.636. So this was our trapezoidal rule approximation, and this is the actual area. So even with just 4 trapezoids, it's not that far off for an approximate value. All right, we're going to set this one up only because the function values get a little intimidating. We're using 6 trapezoids, so that tells me I better have 7 function values. B minus a all over 2 times n. I always start at my a value, and then I double each function value until I get to b. So b minus a over n, I get 3 over 6, which is a 1/2. So the width of each interval will be a 1/2. And that's how I determine the next x value that I would plug into my function. So 1 plus a 1/2, that would give me 3/2, plus 2 times f of 4 halves, which would give me 2. F of 5 halves plus 2. F of 6 halves would be 3 plus 2 f of 7 halves. And then when I add the next half, that would give me 8 over 2, which is 4, which is my b value. So I don't double that. As a check, 1, 2, 3, 4, 5, 6, 7 values that I would have to plug into my integrand. The first coefficients are just 1, and all the middle terms have a coefficient of 2. Now, this would obviously be a calculator problem if I asked you to evaluate it, but we can do this in class. We don't have to take the time to do it now. So this would be the setup. I guess we could, this would evaluate to a fourth, but that's neither here nor there for the setup. You can have it as 1/4 or in that form, b minus a over 2 times n. Okay. Use n is equal to 4, and this appears to be cut off, to approximate this region. We're going to use a trapezoid rule, a left Riemann sum, and a right Riemann sum. Alright, so let's start with the trapezoid rule. So b minus a over n. So the width of each interval will be a half. So my trapezoid rule is a half times that half. F of 0 plus 2 times f of a half plus 2 times f of 1 plus 2 times f of 3 halves, and then when I add another half, that gets me at my b value. Okay, now plugging this into the calculator, this becomes tricky, but f of 0 plus 2, when I plug in 1/2, it would be 1 plus 1/2 cubed. Okay, so the calculator becomes very important that you're able to actually evaluate this. 1 plus 1 cubed plus 2, 1 plus 3 halves cubed, and then plus 1 over square root of 1 plus 2 cubed. Okay, so into the original integrand, I've replaced all the x's with 0, 1/2, 1, 3 halves. When I double them, the 2 times 1 in the numerator is where the numerator of 2 comes from for my middle values, and then I don't double the first and last. And I promise you, this comes out to 1.397. Okay, Riemann sum always means you're going to use rectangles. Okay, so a left Riemann sum, the left-hand side of the rectangle will intersect the function. Alright, so left Riemann delta x is b minus a over n. We're still using 4 figures for each approximation. So on the left, I start at a, and I add 1/2. Oh, I skipped one. Literally the number 1. F of 3 halves. So my left Riemann sum starts at A and ends at f of b minus whatever delta x is. Okay, this approximation, you can verify these. Plugging it into the same integrand is 1.564. And then the right Riemann sum, now this one starts at f of a plus delta x and ends at f of b. So all that changes from the left Riemann sum, we eliminate f of a and in turn add f of b. So this would start at a half, okay. We'll finish this in class tomorrow. I just want to display the homework. Copy that, answer number 1, and please do the problems for number 2.